Alrighty, so if you're watching this on the correct date, Wednesday, June 30th, this should be the day before your first exam. Okay? So this material is not on exam 1, 1, 5, 1, 7, and on will be covered in exam 2. Okay? So last time in 1, 4, we talked about like what is a function, right? And we kind of were using like output at this time, and we didn't really have like a nice way of saying it in a shorter way. So 1, 5 is all about what's called function notation. So the concept is a function as a rule. So the function notation, we are applying something to an input, right? So last section we saw that when we apply a function f to an input, we get a unique output. That's the definition of function. One input sends me to one singular output. It can go to the same output for all different inputs, but as long as one input sends me to one output, good. So we go from how do we get to input? How do we get from input to output? We would say that we would apply f. And f is our function, right? So we can express this symbolically via what is called function notation. And that looks like f, and then we would say, when I saw that parentheses, I would say of input equals output. Okay, so f of input equals output. Here, f is a rule, not a variable of a number. So this is not multiplication, right? And we don't always have to use f. We use f because it's the letter that function starts with. Like we often also see g and h of x, y, whatever. So here, f is a rule, not a variable or number. So that really just saying that it's not multiplying by this variable f. So if x is our input and y is our output, we would then say that f of x equals y. And this is also how sometimes in textbooks and later math classes we'll just say that y is a function of x, and they'll state this. So y equals a function with x in it, right? It's pretty standard. It's like a sentence, right? The good thing about this function notation is I can align my input and my output and which function I'm talking about. So if I have a lot of functions and I want to talk about, okay, when I put in this thing into this function, I get this out. It's a really good naming system, right? So if I consider f of x equals 8 of x, what is my input and what is my output? And then I wrote function question mark. So basically saying, what's the function called, right? So I can see that x is my input, or okay, it's not just my input, it's the input. The output or the outcome of applying f onto x is that I will get 8 times that. So 8x is the output. And then our function is f. So f is the function. Right, so what is f2 and what does it represent? So we would say f of 2 right? So what I'm going to do is I'm just going to plug in 2 for every time all I'm saying here is x is 2. So if instead of writing an x now in my output, I'm going to write a 2. So instead of 8 times x, it's 8 times 2, which is 16. And what does that represent? Well, we would say 16 is the output of the function f. You can say at 2 or when x equals 2. That's the same thing. Okay? So that's kind of why we like made this little bit of put. This is my input, that's my output, f is my function. So then I can say this this number is the output of this function, which is called this thing, when my input is that. So at that input. Okay? So basically replacing y with f of x, but f of x just holds more information. Right? Like when you're telling a story about yourself when you're 5, you would say when I was 5. Now you'd say, oh, I just did this. And then you're talking about something that would be really interesting for you to do now instead of 5 years old. You kind of want to give that little bit more information, and that's what f of x holds versus just saying y. Okay? So now with this more information, I've kind of leaded on to this when we were talking about 1.4, but now we can really define net change a lot nicer instead of saying output this, output that. So with this new notation, we can better define net change. So the net change in the value of f of x changes from A to B is, remember, it's the output of the last one minus the output of the input. Sorry, what? Output of the smaller input, excuse me. So if we're going from A to B, we kind of assume we're going from small to big. You kind of don't talk about net change decreasing in a sense. So if an astronaut, okay, now we're going to do an example. All right, so this is our net change formula now. So if you're ever asked, what is net change? It's that, okay? So if an astronaut weighs 130 pounds, I wish, on the surface of the Earth, then her weight when she's h miles above Earth is given by this function, right? So W is my function, H is my input, this is my output, okay? So this is an example where we don't have F and X, we have weight for W, that's our function, that is dependent on my height above the Earth, so H, or miles above the Earth. And this is just due to gravitational pull. If you've ever, oh my God, I told this story the other day. When I grew up, there was a movie theater we go to, and there was this little moon thing that you could go stand on or tell you're waiting the moon, which, like, looking back on it, I probably didn't need to spend $1 on that, but it was pretty fun and interesting. And I was very confused going to other places because all the movie theaters in town had one of those. And then I found out that that's not normal. So that's kind of that thing if you've ever seen one of those machines. Anyways, so if we evaluate W of 100 and then we're asked what that means. So what does this mean? Now that we're given like some context, weight, h miles above Earth, we can kind of put more explanation into answering that question rather than this is the output when blah, 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 right? So first let's evaluate W of 100. So that's saying that instead of having an H, everywhere I see H, I'm going to put 100. So 130 times 3940, 3940 plus 100, that quantity squared. So that's like 130. Let's see. Oh, my phone died. Okay. It should be 123.67. And then the astronaut weighs 130 pounds. So that means it tells me that weight is in pounds as well. Okay. So then what does this mean? Well, remember, so my input is H. So my input is 100. So we can say, when she is 100, how many units? Miles above the Earth. So stating what my input is and also kind of the context of the problem. And then I'm just going to state the output. She will weigh 123.67 pounds. Okay. And that's it. That's all you need to say. State your input in terms of the problem, then state the output in terms of the problem. Okay. So find the net change in weight from elevation 0 miles to 100 miles. Interpret your results. So net change will be W of, this is like our A to B scenario. So it would be WB minus WA. So B would be here would be like 100 minus W of 0. So I know W of 100 is 123.67. And then W of 0 is actually 130, which you can figure out by plugging 0 into the equation. And also just because we know she weighs 130 on the surface of the Earth. If you're on the surface of the Earth, you're not any more miles above it. You're at 0 miles above the Earth if you're on the Earth. I hope that makes sense. There's a little fruit fly bothering me. So W of 0 is 130. So do minus 130. And that's going to give me negative 6.33 pounds. Okay. And now we're asked to interpret our results. This is similar to the question is, what does this mean? Took another version of saying that. So we can say, oh, from traveling, there's 2 L's in that? Yeah. From traveling, you can say from 0 miles above the Earth to 100 miles above the Earth, or you can just say from traveling 100 miles above the Earth just because she started already at 0. She lost, I'm using lost in parentheses here because she didn't really lose weight. Her mass is the same, but she just gravitationally weighs differently. She lost 6.33 pounds. Right. And that loss we can see because there's a negative, that net change is decreasing. And that's the importance of getting the order correctly on net change, because if not, I'd be like, oh, she gained weight, which is not true. So that's why that's important to get the order of net change correctly. So a ladder one to the bigger input minus the smaller input. So if you're going from A to B, you do F of B minus F of A. Okay. So cool. So now with this function notation, we can kind of expand even more. This is one of my favorite sections. So the domain of a function is a set of all possible inputs. So let's highlight that. That seems very important. All possible inputs for the function, right? Likewise, the range is the set of all possible outputs. So now we kind of define what an input and an output is. So now we can talk about the grand scheme of inputs and outputs. I can also kind of do a selected domain. So I can write a function, comma. So like if I write f of x equals x squared, comma, 0 less than equal to x less than equal to 5. I'm specifying the domain to be when x is between these 0 and 5, including 0 and 5. Okay. That's why we went and like really worked on interval notation and set notation in the beginning of the class. That's why it was important to do that. If not, there would have been a real reason for us to do it. But here's that reasoning why, because we want to talk about domain and range. So I just kind of wanted to make sure that everyone's on the same page of how to express an interval and a set. Okay. So when I write like a function, comma, an interval like that, it's usually expressed in set notation like that with those inequalities. It really means that we can't plug in values for x outside of that domain. It wouldn't make, I don't want to look at it. I'm just looking at that specific little moment. Okay. And that's really important when we talk about specific properties of functions in a little bit. Okay. So you might be thinking in your head, well, like, when can't I plug in a number? When is that? Like, I can always plug in a number. You're about to learn. So there are two instances, and we've kind of already talked about one already. Actually, we've talked about all of them already, that are things I can't put into functions. So for in terms of the first one, 1 divided by x minus 4. So my input is in the denominator. My denominator can never equal 0. Remember that? So I'm going to star this and write so that's kind of the rule that we're kicking in right here, that I can't ever have my denominator equal to 0. So with that, that means that x minus 4 cannot equal 0 because of the star, right? So that also tells me that if I solve this not equality, basically, add 4 to both sides, that would mean x cannot be 4, right? So that's really all you need to say for the domain. Some people do it like, oh, the domain is the set of x such that x does not equal 4. You can write it like that if you really want to, but both of these, just writing x can equal 4 or something like that, that's like the really fancy way of saying it. I'm fine with both. I'm not here to teach you set notation. As long as you know you can't divide by 0 in this next rule, that's what I care about. So then if we talk about number 2, we really talked about this case when we talked about solving power equations. So that one was star. So let's call this like asterisk. And I have the square root of x, right? I can't take even roots of negative numbers, or just negatives, right? So, but I can take the square root of 0. So be careful. I can take the square root of 0, but nothing less than that. Even just 0.00001 less than that, that's a negative number. I can't do that. So only numbers I can plug into g of x equal to square root of x are going to be when x is a positive number, so greater than 0, or equals 0. And we can represent that by just adding the line. So that one we didn't have to do much work to, but that was it. And again, you can even write this as, oh, the domain is 0 to, not negative, infinity, right? These are all ways to do it. This one I could do when x doesn't equal 4. I could be like, oh, negative infinity to 4 union 4 to infinity. That's the whole number line without 4. I unioned, and see these are open brackets. Those don't include 4. They get really, really close on either side, but I'm just not including 4. These are all equal. I'm just really want to emphasize all the different ways that we can write this. Right? So you can write it set notation, interval notation, like that. So in 3 and 4, kind of take it one step further. I'm adding on to it, right? We've got our base. I know I can't, the denominator can't be 0. So if I have a fraction, I'm going to set that denominator and be like, you cannot be 0. And then solve for what x cannot be. And then if I have a root, I'm going to find what x can be to keep that whole expression greater than 0. So for 3, I have f of x equals 1 divided by x times x minus 2. So I know that x minus 2 cannot be 0. So the 0 product property, this comes back to factoring. For that thing to equal 0, one of them has to equal 0. So to make sure that that never equals 0, we need to make sure that each factor can't be 0. So I'm going to say that x can equal 0 and x minus 2 can equal 0, which would then give me x cannot be 2. Okay? So we can say like x cannot be 0 or 2. That's a way of writing it. We could say negative infinity to 0, union 0 to 2, union 2 to infinity. Oh, that's a open bracket. Those looked a little too closed for my comfort on infinity, right? And that follows a similar property here where the union, these are 3 distinct intervals on the number line. Go away that fourth line, yeah. That don't overlap because this is every number leading to 2 on the one side and this is 2 the other side. But I think it's a lot easier to just write that saying x can't be that. So now when g of x equals the square root of x minus 1, again, I just need x minus 1. This little fruit fly is risking its life to annoy me. Okay. So x minus 1 needs to be greater than or equal to 0. It can be equal to 0 if it's not in the denominator. So that means that x needs to be greater or equal to 1. And if you wanted to check it, just plug in something that isn't in there, right? So if I plug in, I need x greater than or equal to 1. Okay, well, 0 doesn't fall into that domain. If I go and plug in 0, I would get the square root of negative 1, which is a big no-no. So that tells me that I'm correct by not including 0. And obviously you can't do that for every number, but it's a good way to check. And then you can also check something that isn't in the domain and be like, oh, that works. I plug in 1 and I get square root of 0, which is good because that's just 0. So I know that x can be 1. X greater than or equal to 1, and that we could write that as 1 to infinity. Really fun. So there's just different ways to write it, the domains. I don't think these are piecewise functions. Before we continue on to talk about piecewise functions, I want to kind of quickly say to an aside, please never write that x equals all real numbers. That's not correct. X is a variable, it's one thing, and all real numbers is a whole set and group of numbers that you're kind of comparing apples to a cornfield, if that makes sense. Like this apple does not equal that cornfield. I could compare apple to corn, but like a whole cornfield, that's kind of different. I could say the domain is all real numbers or the domain is R, just don't say that x equals R. That's a little fuzzy. I can say x doesn't equal these 3 things, or it's just kind of like saying, I don't say x equals that interval. I just say that interval. It's kind of along that lines. R is also that negative infinity to infinity. You can also just say that, but I wouldn't say that x equaled that interval. I hope this makes sense. It's kind of also like we say, we answer in C3, solving those inequalities, and x is going to be, I'm going to have an inequality as my answer to those, but I never say x equals that interval. I just say x is in this interval. I hope that makes sense. I'm saying x is between this and this. I'm not saying x is that entire thing at one time. Okay. I probably overmathed your brain right there. Moving on. So a piecewise function. So this is really harping on, we just learned about function notation so that we could really nicely talk about inputs and outputs, so that we could talk about domains, so that now we can talk about piecewise functions. We're just going up the railings really fast now. So oopsies, I before E except after C, piecewise, I'm like hype right now on these piecewise functions. So a piecewise function, just know us, is a function that is defined by different rules on different parts of the domain. So we've actually already seen one of these, and it's when we were talking about distance in the earlier sections. So we actually already have experienced a piecewise function. It is the absolute value function, right? And we talked about, right, we were just like those bars, x bar if you want to. And remember, if it was a positive number, so if x, so we would say, I draw this like really big set bracket. Only one of them though, it doesn't go on the other side. I don't understand that. So if x is greater than or equal to 0, a positive number, absolute value is just going to spit out that number again, right? Because that's already positive. Absolute value just gives me a positive number. But if x is less than 0, it's a negative number and I want it to be positive. To undo the negative, I multiply by another negative. So I would say that my output is negative x. So my input is x. My output is x if it falls in this domain, or it's this output if x falls in that domain. So that's why it's called a piecewise. I'm piecing together different functions depending on the domain. And there's also really cool things. You can do these things with something called splines, which has like a lot of different piecewise functions, and it's really cool. And it's also really applicable to a lot of things that are going on in the real world. So a really common one is a cell phone plan that has a basic charge of $39 per month, right, including all the fees and whatever. This includes a base of 400 minutes and charges 20 cents for each additional minute of usage. So I don't think this is common now since I think everyone has an unlimited plan, but like it would be like a lot big deal if you ever went over your like 400 minutes or something. So you're going to pay $39 per month no matter how many minutes I use, as long as it's under 400. And that's when you really need to be careful about what the function, the problem is saying. So this includes 400 minutes. So that's telling me I can talk for 400 minutes, including 400, right? Remember how here I have x is greater than or equal to 0, or x is less than 0. That inclusivity is very important. And charges 20 cents for each additional minute of usage. So note the monthly charges are a function of the number of X minutes used. What is that function? So let's call it C for cost, right? So C of X is going to be, draw my big set brackets, my squiggly brackets, God. I guess when you're like a really old math professor, writing those brackets gets kind of a lot easier because I can do them so fast. But then they're pretty messy. Anyways, so I'm charged $39 per month, and that includes 400 minutes. And X is the number of minutes. So if X is less than or equal to 400 minutes, so I stay in my allotted amount, let's also put a lower bound on X. I can't talk a negative amount of minutes. I can't like talk backwards and get back minutes. So let's do from 0 to 400. This is another thing because it also sets you to realistic values of X. Like if I made this function and I included negative values, it would show up on a graph, but in the real world, that doesn't really make sense. So if X is between 0 and 400, I'm in my allotted amount of minutes. So I'm only going to pay that $30. And when we write functions, we don't include units. So dollars a unit, so we won't include that. So we're just going to write 39. Then if X is any second greater than 400, so X is greater than 400, so 415 seconds, so 400.25, I'd have to pay for that minute. So I'm still going to pay that $39. That's my base. I have to pay that anyways. plus for every additional minute, I'm going to pay 20 cents. So I'm talking in dollars. So 20 cents would be 0.2 times the number of minutes over 400. So if I talked for 500 minutes, my additional would be 100. So I took that 500 and what did I do to get to 100? I subtracted 400. So X minus 400. That's the additional minutes. I'm allowed to talk because if I went over 400 and then say I talked for another minute, if I just put X right here without putting 400, it would charge me 20 cents for all 401 minutes, which I only need to be charged for 1 minute over. So that's why we subtract the 400. Okay. And you could distribute and combine like variables if you want, but I think just holding it like this is kind of easy. Okay. So this is our function. We kind of have to talk through all the verbiage that's going on. And I know some people are like, oh my God, the word problems are so hard, but they're kind of the best problems because it makes you think about the stuff in real life. And it also is helpful like in figuring out your phone bill. I think that's useful. Okay, cool. So now we're asked to find a few values. So C of 100. So find C of 100. This is a little bit extra of a step like it was earlier for function notation to just plug it in. I'm not going to plug it into both of them. I first need to check the domain. So check which domain 100 falls in or falls into. And it would be the first one. So 100, we can say 100 is less than or equal to 400. It's just less than 400. So C of 100 equals 39. Okay. And then find C of 400. This is where it becomes very important because you're like, oh, what if I forgot the equal to part of that less than or equal to? Well, then you wouldn't have 400 defined at all. That's your function would not be well defined. Not everything is defined continuously. So, okay, 400. So we can say since 400 is less than or equal to 400, it's equal to 400. C, we would look at still the first one. So still 39. But at 480, I've gone 80 minutes over. So since 480, my input is greater than 400, C of 480 is going to equal 39 plus 0.2 times 480 minus 400, which is the second one right up here, right? So I fell into this domain. So that's my output. And we can see that this is 39 plus 0.2 times 80. And that's another way to, it's kind of walking you through checking that your function that you created makes sense with what the problem was. Okay, great. It's 39 plus, 39 plus 20 cents times the minutes I went over. And I think it's clear to see that if I talked for 480 minutes, when I can only talk for 400, I went 80 minutes over. So good. It made sense that I did X minus 400 instead of maybe what if I put 400 minus X, and then that would show me a different story. So this is just kind of walking us through that. I think this is about like $55. The numbers we wrote make sense to what we're talking about in real world terms. Okay. So this one gets a little wordy, but it's our last one. So it's a pretty interesting problem. And then we're done with 1.5. So a city charges its residents 0.0008 cents per gallon for households that use less than 40 gallons a month. Great. Whew. And it charges 0.12 cents or dollars, not cents, for households that use over 40,000, 4,000 or more. So this amount less than 4,000, this amount, or more. So this is telling me that's a less than. So that's just straight up that. This is this amount or more. So that's telling me greater than or equal to right there. Okay. So find a piecewise model function that models this. I always think it's funny to say it's like find it. Like I'm gonna go out and like look in the bushes for it. No, I'm creating one. Like I guess they're saying you could, but there's lots of ways to do things. There's not one way to do it. So I guess find. I don't know. I think that's silly to say the word find. Anyways, so what do we want to call this one? Do we want to call it C again for because we're being charged things? Sure. You can call it smiley face if you want. What we called it C because I also called it C here. So I like to start with writing my domains first. So something happens that when people use less than 4,000 gallons. I'm going to assume that gallons is our independent variable, right? I mean, it depends on how much I like whatever I use, but the cost depends on how many gallons I use. So if X is, what is it, less than 4,000, and then we have the option if X is greater than or equal to 4,000. So if I'm less than 4,000, if I'm in this first camp, then I'm going to be charged that much per gallon. So I hope it's kind of clear that we're going to do 0.0008 times X because it's like per gallon. I'm multiplying by gallon, so it's just going to give me the amount out. And then 0.012 X for when X is greater than or equal to 4,000. If it's not clear that I just need to multiply by X, come to office hours or email me and we can talk about that. Just this is like $1 per gallon times gallon. The gallons are going to cross out if you've ever done unit conversions, and I'm just going to get a dollar amount back, which I want for cost. So now we're asked to find these things, right? Again, we're just like finding things. So C of 39, so that would fall into this top one. Since 3,900 is less than 4,000. So 0.0008 times 3,900 gallons would cost me, oh, I did an extra zero. Did I? 1, 2, 3, 1, 2, 3. Oh, I meant to do, that's too much of a difference. There's only supposed to be 1 0, or sorry, 2 zeros. Boop. Sorry, everybody. Okay. There we go. So that would cost me $31.50. I don't really want to put my dollars quite yet in there. And then let's do C of 4,200, 4,200, the same thing. That one is now greater than 4,000. So I would do the second function on my list, which would equal 50.40. So now we're asked to interpret our results. We can do this one at a time, or we can do it at the same time. So we can say if we wanted to do it at once, we could say it will cost $31.50 when you're doing these interpretations, or like what do these mean things, you have to use units. You have to. Okay. So if it costs that much and that much to use 3,900 gallons and 4,200 gallons respectively. So great word, respectively. So that would mean the first one goes with the first thing and the second one. So this and this for that and that. So the first this goes to the second that. So the first that, that's confusing. I'm basically pairing these things up together, right? These are being compared or are together, and these two are together. So that's what respectively means. First and second to first and second. Okay. You could also say it costs $31.50 to use 3,900 gallons, and it costs $50.40 to use 4,200 gallons. You know, but respectively is just nice. You can also put a month because we're only in a month time. Okay. So we did a lot of different things in this section in 5.1. If you're watching this on Wednesday, the homework for this won't be due until next Thursday because we have Monday off because for 4th of July. And we have Thursday off for the exam. So this Wednesday class and the next Tuesday class are 2 class periods together that are going to be grouped for a homework. Okay. I don't like to have an exam and then a homework due a few days later. I like to give you guys a little bit of a break. Also give me a break from grading. Okay. So I will see you guys in 1.7.